asked about exam, right? So it'll be what type of exam you want? So you're talking about exam, right? Numerical, no exam. But I think for this class we will have to have an exam. I think. Okay. Maybe I should give an open book, open notes exam, right? No. What's that? Open internet. Then I should give certificate to internet, right? Not to you, right? I think it will be multiple choice question, okay? So more, my questions are mostly applied, will be applied. I haven't prepared yet, okay? So it will be easy, okay? Or if you want, like, match the following, all those things, let me know. Or if you are interested in numerical, that will be easy for me, okay? No? Numerical, how many of you prefer numerical? Some simple density calculation, shape calculation. Only 3 of you are raising hands. How about you guys? Will you be okay with numerical? No? No, I'm asking, yeah. You 3, yeah, and her. So, no, that's okay. Yeah. No, that's okay. I'll give multiple choice question. I haven't prepared yet. Okay. Okay, so any questions from powder flow? Go ahead, yeah.
Entire question will be of MCQ type?
Yeah.
What will be total marks?
What's that?
What the total marks?
Total marks will be, you should ask the total number of questions, right? Maybe 10 or 12. Okay.
That's it.
Yeah, so exam will be easy. Okay. Total marks you can make it up, right? Either 10 or 100 or whatever you want to choose, right? So, okay, so any questions? That's good. Okay, so if not, we'll talk about and coefficient of restitution. Okay, so might be useful for you for coefficient of restitution and friction too, right? So we talked about angle of internal friction, static friction coefficient, etc. Right? So that's used in the pressure calculations, right? We use we will not use angle of internal friction here for most of the stuff except for powder flow and bin design, hopper design, etc. Right? So what are the 2 different types of friction coefficients that we commonly measure?
Static friction and
Sta-
rolling.
okay, common type. Rolling is not very common. Okay, so static and dynamic, right? So static again. Static when the material is starting to flow, that's static. Dynamic again when it's flowing, right? So rolling again when it's rolling. We commonly don't measure rolling, but there will be lots of. We'll talk about effects of rolling on other frictions. Okay. So why friction is important? Why we are to care about friction? Why do we have to measure friction of granular materials, powders, anything?
The effect of flow behavior of the particle.
Okay, one is flow. What else?
Flow behavior also and the time, like how much time it will require to come.
No, there is some major effect from friction. Stress, okay, how it affects stress? Or how, don't go into how it affects stress, but how this will influence whatever we do, this friction coefficient. So what is friction? Okay, distance, no, give me the actual definition, not the distance. How do we calculate friction? What's that? Okay, F equal to mu? Okay, and for normal force, right? So normal force and friction force, right? So now you think, why do we apply that? I've given an example here, car tire, right? So what happens when a tire moves on the road? There will be friction, right? So if there is high friction, what will be the effect on car?
Efficiency will decrease.
What's that?
Car's efficiency will decrease.
Car's efficiency will decrease. You will might see more wear and tear on the tire, right? So it comes back to energy, right? So energy required to move any material will a lot, depend on the friction between the materials. Almost 30% of the energy that we spend to move anything, it could be from car or it could be from, bulk material handling, depends on the friction between surfaces, right? So again, you can take any example, conveying belt, auger, pneumatic, flow of materials, almost all places, whenever it's starting to move, whenever we are moving something, then friction will play a larger role, right? So again, almost all examples, seeds and fruits when we are harvesting, the friction will affect their damage, how it damages the fruits, etc. Okay. So again, friction is opposite to relative velocity, right? So again, this high school physics, you all know that, right? So we calculate using simple formula, right? The tangential force or the friction force is proportional to the static friction or dynamic friction, and then the normal force, right? Again, simple formula, and then the proportionality constant, we get there as the friction coefficient, right? Or coefficient of friction, right? So in general, F is, the friction force is independent of area of contact, okay? But that's, we'll talk about that in a minute, okay? Again, most commonly, the tangential force, the force it takes to move one surface over the other, depends on the type of the material or nature of the materials that are in contact, okay? You would have seen, right? So when you're riding a bike, if you ride on a tar road, or if you are riding on a brick road, or if you are riding on a concrete roads, the amount of pedaling that you have to apply will be different, right? Again, unless, assuming the slope is same, the friction forces will be different. So that's, again, from the surface of, the nature of the material that's used to pave the road, the friction and the energy will also different. So when two materials are in contact, we might assume that they are in contact 100%, right? So that's again the apparent area of contact that we commonly use for most, example calculations, right? But the real, contact will depend on the surface roughness, right? So if it's rough, and again we normally don't get any 100% smooth material. So all the materials will have some amount of roughness. Okay, so the surface roughness will change how this material will move, one over the other. Okay, so what happens is, again, when one surface, for example, one contact on this solid and one contact in this solid, okay, comes in close contact during movement, it initiates a contact. There might be different phenomena occurring when it's moving. Okay, it starts from elastic deformation, right? So elastically deforms, but if the normal force is not very high, it goes along with elastic deformation. Okay, forces are high, then you might see plastic deformation, right? Some materials breaking, right? Some materials on one or the other surface will break, and then sometimes, this surface or one or the other surface can plow through the other surface. That means there is more shearing of materials, right? So all these actions occur when one material goes, or moves over the other material. That's why to overcome these contacts, you will need lots of energy. Okay, that's why we spend, again, lots of energy to, again, overcome this addition bonding. So if it's same material, then there will be cohesive bonding. If the materials are different, then there will be addition bonding that depends on the molecular level interactions. Okay, so the type of chemical composition, for example, on the food materials will depend or will define these, molecular interaction when two surfaces comes in contact. So once the contact is almost ending, you know, the separates, the bonding separates, okay, the addition or cohesive bonding separates, and then there will be some elastic recovery, okay. So, but if there is plastic deformation, then you lose those, you will not regain, but whatever elastically deformed, we regain that, the material regains, right. So in general, if you take a closer look or time and force, you know, you will see a stick slip motion due to tons of different asperities present on the surface of the material. You know, it sticks, there will be bonding, then it slips, you know, regains it, you know, elastic deformation is regained, and then again it sticks, slips, etc. Okay. Just as an example, you know, if tire moves on the road surface, okay, there will be continuous of the stick slip motions, you know, that's occurring, or slip forces occurring on the surface of the material. Okay. So how many of you ate bread this morning? Bread, slice of bread. No one? No one used bread? You all are healthy? So how many of you eat bread, or yesterday or last week? So what did you eat with bread very commonly? Jam or butter, right? So when you cut butter, you know, you will see this. Easy to notice this, the effect of friction, this adhesive cohesive bonding, and then finally shearing on the surface of butter. Okay. Very easy to observe, but other surfaces, you know, you may not be able to observe, but you know, very common. And another general question: how many of you walk? You know, how many of you visited a snow place, snowy region, Jammu Kashmir, Himachal? Any of you? No. Any? You are? Okay. So, did you walk on ice? Ice? Okay. So why you slip when you walk on ice?
Because friction.
Friction. Why? That's what. Friction. Yes.
Because ice surface and our shoe surface is friction between them.
But our ice is solid, right? So why the friction is low?
That time moisture content will higher now. When we suppose I'm pressing the ice.
Yeah.
So some melting.
Okay, that's very good, excellent answer. So when you walk on ice, you know, usually for ice there will be a thin layer of water surface. So that's what reduces the friction. That's why when you walk on ice, you slip and fall. But that's well fine. Now, there are some recent findings that said, you know, on top of ice, the molecular, you know, structure is not uniform on the crystalline solid. It's a crystalline, right? So that's why you slip more when you walk on, you know, ice. Okay. Again, coming back, you know, that's again friction effect from the change in molecular level, you know, structure on the surface. Okay. So traditional friction measurements. So how do we measure, right? Many of you would have used this kind of setup, right? Yes or no? For grains at least. So you put some amount of samples that you know the normal force, right? And you slowly slide the platform. So at specific angle it starts moving, right? The whole container with the grains or materials will start moving, and at the place that, you know, at the angle at which it starts moving gives you the coefficient of friction, right? Many of you would have measured, right? So that's very common. Go ahead, you had a question? No. So, and or if not, you know, again, you know, if you wanted to measure between grains and a larger granular material to plate, again, same observation. You attach the plate, you know, make the grains move above different surface and get the angle at which you get, you know, the grains are moving, and you get the coefficient of friction. Okay. So again, that's static and both dynamic, right? So you can, at the initial force or initial angle that at which it slightly moves will be the static friction coefficient, and the angle at which it keeps on moving, it will be the dynamic coefficient of friction, right? So what will be one major disadvantage of this setup? What could go wrong? From the grain side, okay, don't think about instrument. Any thoughts?
It does not measure internal angle of rotation.
Yeah, we don't have to worry about internal angle. It's just the
particle to particle.
particle to particle. Not really. So
For cube shapes, it may not fall.
still, you don't have to fall. It has to just move, right?
The layer of grains, like it may happen like top layer of grain may fall first, or the bottom layer may fall, but top will go.
That we are not moving from. Yeah, so that might be, but still that gives a friction, right? So we generally take one layer moving. Okay, that's not a big disadvantage for the method per se. Okay. Any other thought? What happens here at the bottom, at the contact between the grain and the sample? What happens is sometimes this can roll inside, right? So again, we are not accurately quantifying the friction between the surface, but there will be some effect of rolling of the materials. Okay, so we all do this measurement, but may not be accurate. For your research, if you want to measure friction, this may not be the appropriate method. Okay. So another method, we use this Instron or MTS machines. What we do is connect to the Instron testing machine and make the grains move through the surface. Again, this is done by one of my I was talking to some of you, right? We give project works for all students. So this is a third-year level students who did this project on measuring friction of soybeans, okay, or different grains. So you can see the grains are not, only the grains are touching the platform, and then the force at which it moves, right? Initially and also when it continuously moves. So same disadvantage is here too. So the grains inside can roll, right? So you are not accurately quantifying the static and dynamic coefficient of friction. There will be more effect from rolling coefficient of friction. Okay, but you get a nice graph. The peak will give the value of static friction coefficient, and once that's the dynamic coefficient of friction. Okay, but and again easy and simple example. So on the instrument side, what could be one disadvantage of this method from the instrument side? Any thoughts? And you can guess something from the instrument side. So you're measuring friction, right? So that's a clue. So what could go, what could be one thing wrong in this setup? Or what, it's not wrong, but what could be one thing that does not give us exact, accurate quantification of friction? Any thoughts? Quick? No? Okay. So you're using a roller here, right? So it adds to friction. So the roller should be absolutely frictionless, so that you are quantifying just the friction of material. If not, you will be adding this friction effect to the grains or to the materials. Okay. Same thing, this wire, it should be very stiff. You cannot use some loose strings and straws, because then you are adding force to move that straw or straighten that straw or string that's attached. So it has to be absolutely stiff when measuring. Okay. Friction measurement by shear plates, again, similar to shear test instruments, you can use shear plates. So there will be two plates. Again, you put the powder or grains inside and move one plate over the other. Okay, and then again you get the forces acting between those plates. And same disadvantage can happen here by the rolling of the material inside. So if it rolls, then your accuracy goes down. Okay, or the old setup that I talked about using Instron, you can move both the surfaces. So you can avoid little bit rolling effect here. If you're if you're moving both of those across, but still, it's not very accurate method. So some others modified it a little bit. Attached the grains of material that you wanted to measure the friction. Instead of moving those, you move the test material through those grains. then you little bit avoid the effect of rolling or moving of grains, when you measure the friction. Okay. And again, very similar to the shear setup. So, it's again baffle that goes into it, and the grains, when the baffles moves over the grain surface, you measure the friction. Okay. So, there are tons of, friction setup measurements that you can develop and use, but there will be some disadvantages. Again, same disadvantage, you will see those, movement of materials or rolling of materials that will affect your friction measurement. Okay. But how can we accurately quantify friction? It's difficult, right? So as the method C. But general, if you're using a tribometer, okay, you might get some more accurate measurements of friction. Okay. So tribometer, again, very minute measurement of forces on the surface. Again, this is from one of my past research. So we wanted to measure the friction on wheat kernels. Okay. So you measure the force when the surface moves over the wheat kernels. And again, it's not a large range of movement, it's very small movement, like 5 micron, 10 micron, movement. And then, it's kind of back and forth movements, and then you can get, friction coefficients. We use the same setup for friction measurements and also wear on surfaces, how much you lose when two surfaces comes in, contact, mainly from friction effects. Okay. So again, same setup, from the peak values you get the static friction, and then from the plateaued value or the constant force you get the dynamic coefficient of friction. Okay. Maybe the central lab facility may have this a tribometer here. If you are working on friction measurements, maybe you can check with them. Okay. So it's easy to modify those, again in this setup. So my student, most of it, he 3D printed the surfaces and then used them, attached them, and then measured those. Okay. So again, it affects many of those conveyance and energy needed to convey. And when it comes to modeling, it plays a big role. Okay, so you'll have to know the accurate friction values when you are, especially when you are using discrete element method models. Right? Any questions?
So that device that will move like this or harmonic motion.
Usually one direction, but I think depends on the instrument type. You can have both directions too. Okay.
Straight plane, we can measure in straight plane also, or we have to.
No, it's straight plane. So you are just measuring the force, right?
Yes, sir.
So you don't have to incline the plane. So you just have to measure the friction. Yeah? What's that?
Can you explain again tribometer?
For tribometer, it's again, it's mainly used for measuring the wear on surfaces. So for example, that tire companies, metal companies, they want to know how much they lose by wear, right? Or so we modified that setup a little to find, calculate the friction. So wear means again rubbing of one surface over the other, right? So you rub it for like 1 hour, you lose some materials, you get the wear, or you rub it for like 1 day, then the wear will be different, right? So it basically you can adjust the force acting on the surface, and then you get the friction. So what we did was like, what my student did was like he attached some kernels on the bottom of that, and then this is a tribometer that measures, the surface that measures the, force acting on that surface. Okay, so it kind of moves on the surface and get the forces. Okay. So for grain to grain, what he did was he attached some grains on the bottom of this. Okay, so it's not, I'm not showing the picture. So maybe if you look very closely, you'll see a wheat kernel on the bottom here, so on the blue, below the blue. So attached a wheat kernel on the bottom, you just glue it, and then measure, you can measure, grain to grain or surface to surface that is of interest to you. Okay. So clear?
But in case of powder, sir, which method we follow for accuracy?
that's a very good question. Powder, for modeling or for, use? In general, it's, it's very difficult. Shear plate method is common, okay, for powders. Okay. So shear plate method, these are for larger, granular materials, but shear plate you can use for, powders too. Okay. Any questions? Okay. So there are some references, and let's talk about coefficient of restitution. So except you, how many of you heard about coefficient of restitution? No one. So can you guess what could be coefficient of restitution from this picture? It's more useful when you model, but in actual purposes, go ahead, yeah, tell. Can you guess what is coefficient of restitution from the picture? As I said, you cannot give wrong answers tomorrow during the exam, okay? But you can have wild guesses in the class. Yeah, you have an answer, right? Yeah, that's it.
That the energy is decreasing in heat.
Okay, yeah, that's the answer. The energy lost. So energy lost during impact. Okay, so I'm just giving bouncing of basketball example. So when you bounce a basketball, when you leave bouncing, what happens? It slowly comes to a stop, right? So it losing energy. By losing energy, coming to a stop, right? So it's important mostly when we model, using different discrete element methods or other modeling techniques, just to see when two particles collide, how much energy is lost. Okay, when two granular material collide, how much energy they lose or how much energy they absorb, and then how it affects their handling and processing behavior. Okay, so the simple way is getting, again, as I said, simple way is measuring the energy before and after collision. Okay, so before and after collision, we get the energy, and then from the energy lost, we get the coefficient of restitution. Okay. Okay, yeah, I don't have that there. So one question. Okay, so what is the major assumption here between the two particles? Depending, the nature of the particles. So we are measuring the collision before and after, right? So what could be one major assumption that helps us getting those loss in energy during collision?
Point of contact.
What's that?
Point of contact.
Yeah, point of contact will be uniform, that we assume that it's uniform.
Elasticity of particle.
Yeah, so it's go yeah.
Plasticity.
Yeah, that's we assume that it's elastic.
Elasticity.
Okay, so if it's plastic, what happens? When during collision, it loses some material, right? So other than energy, we are losing some material. So we assume that it's elastic, and it's normal contact between those. Contact, we assume normal contact. Okay. Measure in general based on the velocity before and after impact. Okay, I'll show you some setups. So using the velocity before and after impact, we calculate the energy lost or the coefficient of restitution. Okay. So in general, at higher velocities, the effect will be 0. The coefficient of restitution will be close to 0. Okay, but in lower velocities, it might different. Okay, so I'll talk about that in a minute. Okay, so energy, again, there are different ways. One is mainly from energy lost and the velocity, right? There are different setups to measure. One is based on impact or collision. So you make the material collide, and from the change in height before and after collision, you get the coefficient of restitution. So the change in height or the distance it travels after collision is directly dependent on the energy it's losing, right? If it's not losing a lot of energy, it comes back. If it's losing energy, then if it's losing lots of energy, the distance it travels will be very low, right? Is that clear? So you can, there are different modified setups to get from particle to particle or particle to wall surface. So the idea is same, depending on it, how much distance it moves, you get the, coefficient of restitution. Okay. Common setup, again, free fall experiments. So what happens is, you make the material drop from a specific height, okay, and you use some high speed camera to get the rebound velocity. Okay, you know the velocity when it falls from a specific height, and from the rebound, by using rebound velocity or rebound height, you get the coefficient of restitution. Okay, simple setups, right? So what will be one major disadvantage of this setup?
So it is difficult to catch the particle of rebound particle in high speed camera also.
No, you can still catch. It's easy. High speed camera, I know it depends on the FPS, right? For frame per seconds. If you adjust frame per seconds,
Yes, sir. And one more thing, sir, it changes from particle to particle. Sorry, like
What is?
for some particle it rebound height will be low.
Yeah, so
And
it's
for
not.
some it will be high.
Yeah, it will never be the same, right?
It
So
will never be the same.
so that's not a big disadvantage too. So that's what we are quantifying, right? Anyone? Any wild guess? So for example, you are dropping a wheat kernel, okay, from this height. So will it rebound in the same orientation? No, right? So the orientation of rebound can change, right? So that means, that grains can roll, right? So when it rolls or when it changes angle, then you lose some energy for that rolling or changing in angle, right? So we are not exactly quantifying the restitution because some energy is lost with rolling or change in angle. So this is always, it's highly used, but it's not, useful when it comes to getting the actual, accurate coefficient of restitution. Okay, since there will be lots of rolling. Okay. This again, what one of my student did for grains. What he did was, like, from dropping experiments, he dropped the grains from specific heights into different bins, and based on the distance it traveled across different bins, he quantified the restitution coefficient. Okay, again, he plotted, lots of things. I'm not, maybe you would have seen the paper, but if you see the paper, there are, lots of other calculation that goes in, into that. So based on the average bin number, or how much it travels, okay, again, there will be some rolling too, right? But since the plate is slanted, we thought we are accounting for the rolling a little bit, but still there will be lots of, from, rolling off those grain kernels, but you can get some decent value better than, free fall experiments or by impact experiments. Okay, little better, measurements. Okay, but again, the major challenges is, very weakly depends on velocity. So for some effects, for some heights, the velocity effect will be high, but again, over a period of time, when you change the velocity, the effect might be, very poor, or the relationship might be very poor. So when you quantify those restitution, then you may not get accurate values. If you change the height, drop height, or you change the impact height, then you might not see any difference in change in restitution coefficient. Okay. One other challenge will be heat generated during those elastic deformations. So if you during impact, there will be some heat generation, right? So if by any chance, if there is some heat during that interaction, then you're losing some energy on heat, right? So you're not accurately quantifying the energy for impact or energy on, rebound height. There are again lots of examples on measurements or some published papers. Okay. So how do we measure for powders? Again, I will come back to that question. We can easily measure for large granular material, right? But how will we measure for powders, coefficient of restitution? Any thoughts? How can we measure restitution for powders, small powders? Go back to the example of wheat flour. You wanted to measure the restitution for wheat flour. Any thoughts? Come on, give some answer. No answers? Okay, so I will give the answer. We don't measure. Okay, it's very difficult to measure for small materials. Okay, so we assume. So when you are doing modeling, you simulate with range of restitution coefficient values, and through experimental validation, you find the appropriate coefficient of restitution. For larger materials too, we talked about lots of challenges, right, for measuring coefficient of restitution. So most simulations, when you see those papers, they don't measure. They, do some, calibration of parameters. So, model parameter calibration is also, very important and big. So they calibrate some of those properties, such as, coefficient of restitution, Young's modulus. Young's modulus a little bit, maybe you can measure, not for small materials, but for large materials you can measure. But Young's modulus, coefficient of restitution, Young's modulus, Poisson's ratio, etc., very difficult to measure accurately. So what we do is, you assume some starting value and then keep on doing simulations and calibrate with some simple experiments, like angle of repose or bulk density measurement, etc. Okay. So when you get the exact angle of repose or exact bulk density same as the simulation, then we assume that the values that we took or used for that simulation will be appropriate. So okay. It's not the accurate method, that's the way we can do. Okay. Okay, so any other questions? There's one more lecture pending, right? So we'll talk about some compact property measurements, okay? So before going into that, so Prashant, what time is lunch? 1:30, okay, we have time, some time, right? So next lecture is also not very long, it will be short lecture, okay? So what's your feedback? What did you learn from this? Not from this lecture, overall, 4 days.
We learned a lot about the particle flow behavior.
Okay,
It was not covered in our MTech syllabus, so we learned a lot about
okay,
it will be work some industry and also we can apply this.
okay, definitely, okay. Give me both positive and negative feedbacks too, okay? So what will be one negative feedback?
Also there is no negative.
Yeah, that's okay, you can, Hey, don't go that far, we'll start the next lecture soon, okay? No, yes. Yeah, you can stop.